Hello and welcome to this first tutorial in a series on quadratic functions, which loosely speaking is the study of beautiful curves that we call parabolas. Now, if there's any one topic in the maths curriculum at this level that causes the most difficulty for students, I think it has to be this one. I think the reason students find it so difficult is that it actually has quite a number of different aspects to it, and they're often taught separately. So my aim in this series of tutorials is probably going to be about 6, roughly speaking, is to give you, hopefully, an integrated, coherent, clear view of the whole topic, so that you'll see how all these little pieces are related very kind of nicely, actually, so that you might even come to enjoy this topic, but certainly that you understand it and feel confident. Now, I'm not going to go through all the topics in the series right now, but if you look in the description below the video, you'll see little subtitles for each tutorial in this series, and you'll be able to see which of the smaller topics that they cover under quadratic functions. My aim in this first tutorial is to give you an introduction to parabolas, and that will already introduce a number of really fundamental concepts in an easy to understand manner, and I think it will give us a good foundation then for being a bit more formal in the second and subsequent tutorials. So that's the plan. So the topic then is quadratic functions. And as I say, my aim here is to give an introduction. So let's write down the simplest quadratic function we can, which is the following: y equals x squared. And let's just see what it looks like. So let's draw some axes, x and y, the origin, and this is similar to what we did with straight lines. It's just to kind of use our bare hands, as it were, to craft what do the functions actually look like, because if you're able to sort of build the function yourself just in a sketch, you sort of own it, and I think it gives you much more confidence. So let's just see what happens. This equation is telling us that y is given by the square of x. It's an instruction. We can just take different values of x along this number line, this x-axis, and see what values of y we're instructed to put coordinates to, and then we'll trace out a line. So we're told when x is 0, we have to square that to get y, and 0 squared is 0. So this curve is going to pass through the origin. When x is 1, 1 squared is 1. So that's pretty straightforward. Okay, so there's y equals 1. We have a point there. Now look, when x is negative 1, and we square negative 1, we also get 1. So when x is negative 1, we also go 1 unit above, and there'll be a point there. When x is 2, we square that to get y. 2 squared is 4, so we need to go 4 units above. So 1, 2, 3, 4. It's kind of up here, roughly speaking. And again, this is just meant to be a sketch. So roughly speaking, this curve's going to go through that point. And then let's just do x equals negative 2. We square that. We also get 4. So we're already seeing an important aspect of parabolas here. So those are a number of points, and we can join these up, and let's see what happens. Now again, my sketch is not going to be so great here because I can't tilt the paper, but I'm just going to try my best to plot this. Okay, it's not too bad. That is a parabola, and we've built it with our hands. There it is. The most important thing that I want you to see, and this will be true of every single parabola, is that it has a symmetry. In this case, do you see that the y-axis itself is like a mirror? And if we sort of placed a mirror on the y-axis and we're looking in from this direction, we would simply see this other half of the curve. And the reason's pretty straightforward actually, which is that whatever number I take on the positive side of the origin and square it, I'm going to get the same value for y if I take the equivalent but negative number on the left-hand side of 0. The function x squared gives you the same value whether you take a positive or an equivalent negative value of x, and that gives us this symmetry. Every parabola that we look at will have a symmetry, and it's one of the most important properties that we should know about, and also that we're going to be examined on. So that's y equals x squared. Let's just do another one, shall we? Let's draw another coordinate axes here. X and y. You might think, why am I drawing it like that? But it's because I want to look at the curve y equals negative x squared. Okay, there's the origin, there's 1, there's 2, negative 1, negative 2. Now I'm going to do this pretty quickly because we've already done y equals x squared. All we're doing differently is putting a negative sign in front. So whereas before we got, for example, y equals 1 or y equals 4, sorry, I should have written 4 up there, we're just going to get the negative of those. So when x is 0, 0 squared is 0, take the negative sign, negative 0 is still 0, so the curve will pass through the origin. When x is 1 or negative 1, the square will give 1. We're then multiplying this by effectively minus 1, and y equals negative 1 will be the value for those 2 points. When x is 2 or negative 2, we square that, we get 4. We then multiply by this negative 1, and that will give us negative 4, which is sort of down here, roughly speaking. There's negative 4, and so we'll have a point here and a point here. I can then draw my parabola. Not too bad. It's not really a very good sketch, that one. Never mind. Essentially though, it's the same curve as this, but flipped over. You might describe this as sort of a valley shape and this as a hill shape. Again, notice that the y-axis acts as a mirror. The curve on this side is the mirror image of the curve on this side. Right. Generally, we can talk about curves that have y equals a number, let's call the number a, times x squared. And what I want you to really grasp here is the following, that for any curve y equals ax squared, if a is positive, do you see that y will always be greater than or equal to 0? It's going to be just like this. The curvature may be a little bit different, but it's going to have this valley shape, and it's never going to be negative, because whatever value of x we take, x squared is greater than or equal to 0. We're saying that a is positive, so y will always be greater than or equal to 0. Y equals ax squared will always look like this. Okay, if you have a large value of a, it might be more sort of pronounced like this, and if you have a small value of a, it might be a very shallow valley, but it's always going to be a valley, and it will always be symmetric about the y-axis. Similarly, if we have y equals ax squared and a is negative, then x squared is always greater than or equal to 0. If a is negative, we're multiplying that by a negative number. Y will always be less than or equal to 0. And we will have curves that look like this. Okay? essentially a hill shape. So this is something, we've already got two quite important concepts with quadratic functions, aka parabolas. They always have a symmetry. The ones I've drawn are all symmetric about the y-axis. And the number that multiplies x squared, the sign of it is very important. If the number multiplying x squared is positive, you'll always have a valley-shaped parabola, and if the number multiplying x squared is negative, you will always have a hill-shaped. So ax squared with a positive, the curve has a minimum somewhere. Ax squared with a negative, the curve will have a maximum value somewhere. Okay, but we'll talk more about that in later tutorials. Right, I'm just going to sketch a few more parabolas in the remainder of this tutorial. Let me, just for the sake of argument, restrict my attention to a positive. It's not going to sort of constrain any of the ideas that I'm going to give. Those ideas will be true for a negative too, but because I want to sketch some examples, I have to sort of choose a sign of a, and I'm just going to choose a to be positive. And let's see, we've already got y equals x squared, so let's just plot another one. Let's plot y equals x squared plus 1, okay, and see what we get. So there's x, there's y, there's the origin. Now notice now when I set x to 0, I get y equals 0 squared plus 1, which is just 1. So at the origin, the curve is going to pass through a point 1 here, okay? And then, if x is plus or minus 1, the square of that is 1, and then I'm adding 1, I'm going to get 2. So this curve at x equals negative 1 or 1 is going to pass through y equals 2. So I'm going to have a point here, a point here, and a point here. And let me just then do negative 2 and 2, these sketches here. It's quite good to sketch on plain paper. Obviously it's easier to sketch on sort of graph paper, but I think it's good practice just to not worry too much about exact details, but focus more on the kind of the general shape of things. Because, as I've said a number of times in these tutorials, maths is often about patterns and shapes rather than about exact numbers. So if x is plus or minus 2, x squared will be 4. We're adding 1, we're going to get 5. So 3, 4, 5, we're going to sort of be up here somewhere. And at x equals plus or minus 2, the curve is going to pass through these 2 points. Let's see if I can join these up nicely to make a parabola. Not too bad. That's not too bad. Okay. Right. What's the key point from doing this? Well, very similar to this curve, but it's just been shifted up by 1 unit. Okay. It's symmetric still. So let me just put the word symmetry here in big writing in the middle of the page as kind of one of the really big points that we're getting from this. I like to think of this as a mirror, actually. So there's a mirror always in the very center of our parabola. So the mirror in all of these examples I've drawn is the y-axis itself. By adding 1 with this particular parabola, all I've done really is just shift the curve up, so it doesn't seem terribly exciting. Okay, let's do another one. Let me look at y equals x squared to take away 1. Okay, let's see what happens with that. X and y, there's the origin. Now, if x equals 0 now, y is negative 1. So at x equals 0, y is negative 1, so the curve's going to pass through there. Now if x is plus or minus 1, x squared is 1, I'm then taking 1 away, y will be 0. So at x equals negative 1 or positive 1, I get that y is 0, so the curve's going to pass through those points. And then at x equals plus or minus 2, x squared is 4, I take away 1, I get 3. So I have 1, 2, 3, so roughly speaking there, come across, and then I've got negative 2, plus 2, and my curve is going to have these points too. So at x equals plus or minus 2, y will be 3. And let me try and draw this. Yeah, I haven't drawn that terribly well. What's hard to draw with parabolas is to get the nice curvature, but that's good enough for our purposes. Yes, it still has that symmetry. If I had drawn it better, it would have a nice mirror symmetry there. The key thing, though, that I want you to see from this sketch is, and I'm going to use a different coloured pen, this curve, y equals x squared take away 1. So let me just draw it again there, write it again there. Y equals x squared minus 1 is the curve that I'm drawing. Notice that it cuts through the x-axis in 2 places. And we are now going to get several concepts from this simple example that we are going to be following for much of this topic. When a function like a quadratic function, if that curve cuts through the axis, we have a special name for the x values where that occurs. We call them roots. So R-O-O-T-S. We call those roots. And we see we have 2 roots here. One there and one there. Okay? Also, because of the symmetry, the roots, and I'll write this in words, the roots occur equidistant from the mirror. Okay? Now that mirror that I've been talking about, that sort of line of symmetry, has a more formal name. The mirror is sometimes called the axis of symmetry. Okay? But the concept that I want you to get from these simple sketches is that if the curve has roots, because look, this curve didn't have any roots, this curve does, has 2. If there are roots, they will be equidistant from the mirror, i.e. from the axis of symmetry. That's interesting because that tells you something. If someone told you, I have a parabola with roots at x equals 2 and x equals 4, you automatically know that because those roots have to be equidistant from the mirror in that case must be at x equals 3. The mirror will lie midway between the roots. Okay? So, just generalizing what we've done here to thinking about y equals ax squared, I want you just to think about y equals ax squared plus a constant. Okay? And let's just think of a positive. Then we have 2 main possibilities. Okay? We know that if we have c equals 0, we've already discussed that, that's what these curves look like. If I add on a positive value of c, it's going to push these curves up. So if c is positive, I'm going to have parabolas that look like this. Okay? And you see, those parabolas have no roots. On the other hand, if I choose c negative, I've got a curve like this with c equals 0. Adding a negative value pulls it down, just like we saw with x squared negative 1. It pulls this function below the x-axis, and I'm going to have parabolas that look like this. They're both symmetric about the y-axis, this one has roots and this one does not have roots. So there are the two roots. Notice they are equidistant from the mirror here. So just by looking at really simple examples like we've done here and just sketching them, we've actually brought out all of the main concepts in this topic of quadratic functions. The main concepts are that all parabolas will be symmetric about a line, an axis, which we can call the axis of symmetry. I kind of informally call it a mirror. If we write parabolas y equals ax squared, then if a is positive, they will be valley-shaped, and if a is negative, they will be hill-shaped. So the valley-shaped parabolas will have a minimum value somewhere, the hill-shaped functions will have a maximum value somewhere. If we add a constant on to parabolas that look like ax squared, we either push them up, okay, or we pull them down. In the case when a is positive, when we have a valley-shaped parabola, if we push them up, the curve never sees the x-axis. If we pull them down, the curve cuts through the x-axis twice, and where it cuts, we call those values of x roots, and they'll always be equidistant from the axis of symmetry, from the mirror. You notice in this case that the curve just touches the x-axis at one point at the origin, and that is also a root of that function, and we'll talk more about that in the next tutorial. So I'm going to stop there. This introduction was meant to give you confidence with a number of key concepts from just getting your hands on the functions and plotting them before we get into more sort of technical terminology and methods. But the rest of this subject really is about introducing a number of tools so that if someone gives you a quadratic function, instead of plotting it really carefully, you're able to use these tools to immediately work out things like the axis of symmetry and the roots and so on and so forth. So I hope this first tutorial has been helpful, and I'll see you next time.